Hello, ladies and gentlemen, and thank you for standing by. Welcome to this ASM webinar, Grain Size, Then and Now. I'm Vicki Burt, editor with ASM International, and we're glad you could join us. Today's presentation is part of the ASM webinar series designed to provide information you can apply to improve quality, efficiency, and performance. This webinar series supports the needs of our members, customers, and the materials community at large. This series also supports the outreach needs of the leading corporate supporters of ASM and its affiliate societies. The sponsors of today's webinar is Clemex Technologies. Since 1990, Clemex has been at the forefront of high-end image analysis, developing solutions for the characterization and analysis of microstructures. In recent years, emphasis has been placed on machine learning algorithms, enabling customers to go beyond the limits of traditional imaging methods. Clemex specializes in the integration of advanced computer vision, building out tailor-made software and hardware solutions that best suit clients' needs. Clemex exclusively uses leading brands of microscopes, stages, and cameras in order to uphold unwavering commitment to delivering high-quality results. We're proud to have Clemex Technologies on board for today's webinar. Before we begin, let me mention a few housekeeping issues. If you're having technical difficulties in joining the GoToWebinar session, dial 877-582-7011. All participants will be in a listen-only mode during the presentation. Feel free to submit written questions at any time by using the Q&A window located in the upper right corner of your screen. Click the question mark button to open the Q&A window, type your question in the box at the bottom, and click the Send button. We'll answer as many questions as we can at the end of the webinar. We're proud to host today's webinar. For over 100 years, ASM International has served the materials community by providing scientific, engineering, and technical information, as well as education, networking, and professional development. Advanced Materials and Processes is ASM's flagship technical magazine. It provides information about leading-edge developments and trends in engineering materials and the methods used to select, process, fabricate, test, and characterize them. The magazine also covers emerging technologies such as nanotechnology, additive manufacturing, and management topics of interest to scientists and engineers. With that, I'd like to introduce the instructor of today's webinar, Marc Lavallee. Marc has a metallurgical degree from Trois-Rivières, Quebec City, Canada. He worked as a metallurgist in both an aluminum foundry and a cast iron foundry. He also worked at Buehler for 13 years as a sales engineer for sample preparation equipment. Marc has been at Clemex since 1997 as a business development manager, initially distributing sample preparation equipment in Canada. His sales involved not only sample preparation equipment, but also method development for his customers. Eventually, his sales role became focused on image analysis products and Clemex core products with a worldwide reach. Marc has developed deep knowledge in image analysis at Clemex for multiple industrial applications over his 23 years at Clemex. He has worked in various fields of interest, including metallurgy for applications like grain size, layer thickness, and inclusion rating, aerospace, automotive, and medical devices for cleanliness applications, pharmaceutical applications on particle size, as well as electronic applications. It is a pleasure for me to introduce Marc.
Well, thank you very much, Vicki. Thank you very much for the nice introduction, and thank you all for joining us on this webinar on grain size measuring method. I'm just gonna start this. All right. So we'll look at traditional methods, and how it's done as per the standard, and also we'll look at how modern image analysis systems integrate them, and some new approach that are made available by the technology. So we'll have a quick overview of Clemex. Basically, as Vicky said, we've been there for 30 years. It was founded by some very knowledgeable imaging people, and they created it's called Vision PE image analysis software. It's our flagship software. And I'm getting a feedback here. I'm not sure why. And also we're integrator of image analysis solutions. So basically we integrate microscopes to make it as a full solution. So we're basically specialists in image quantification. Sorry, my button is not behaving. So we're covering many fields of applications, metallurgy being one of them, because this is what we're going to talk about today. So grain size is one of them. So if we look at I'm just going to put my laser point. So we have a different type of grain size, aluminum, those are carbides, but also image analysis could be something similar to this, where we have a white background and dark features. So in this case here, silicon carbide and aluminum, but it could also be nodules like graphite into steel matrix, cast iron matrix. So it's kind of similar. We can do inclusion rating. So again, we have dark feature into white background. So it's kind of similar. And but we can also address a non-metallurgical application, like this is cotton here or polymers. So basically what we're looking for are something that we can focus on. And in this case, like the border of these feature here, for example, would be detected. And then you end up with measuring the size of the cotton fiber. If we look at where we have a cell size measurement, it looks like a grain size. It's still the same principle. We can do some life science also, color imaging. If we look at an artery here, we would be measuring the layer thickness of fat, but we could also compare it to a coating thickness on the jet blade. It's also a coating, right? So an integrated image analysis system means that we have a software that will do the measurements, but also that will control the microscope and a motorized stage, so we can scan a larger area, so that we have better statistics to rely on. So basically, we integrate all of this hardware together: cameras, motorized microscope, stage controller, imaging, all as one piece. So it's one solution, and so we can work with the Nikon microscope, Leica, and retrofit some other ones like Olympus that are existing. That are existing systems, should I say. We also can import images from SEM. So I remember working on grain size, ceramic grain size from an SEM system. So it works the same way. Why do we measure grain size? Grain size has an effect on most mechanical properties. So everything that has a room temperature, that is working at room temperature, generally that are used in the industry. So temperature, hardness, fatigue, yield strength, all of these things will increase by decreasing the grain size. So the smaller the grain, the tougher it is. Another example is machinability. So if you have rough grains, it will be easier to machine. But if you have a good finish, it will be better with a fine grain size. Now, to measure grain size, there are various methods, but overall, the idea of measuring grain size is just that we're measuring what we see here because we're of their purely geometric basis. So that means that whatever we could measure other things than grain size with a grain size method, like the one that we will be talking about. So you will see some example afterward. So what we're saying here is that we can estimate the average grain size, crystal or cell size of non-metallic materials, the same way as we would do for grain size. So generally the approach is to use a comparison method. using charts, but we can use the more accurate, if you want, intercept and planometric methods. And because grain size, I mean the charts cannot be used with the measurement of individual grains, which is sometimes what we're looking for. So before we get into the measurement, we should have a quick look at the the sample preparation, because it's quite important. If we don't want to distort the grains, we need to make sure that the material will be not deformed. So when we cut the material, we cut the original sample, we need to have a proper cutoff wheel so we avoid excessive deformation. The mounting is important, but not necessarily. Sometimes you could work with a unmounted sample and still, of course, get some grain size, grind and polishing, which is the next step. Now, what's important here is that we have to end up with a good sample preparation, and the reason is not just to have a final nice finish, but also to remove any residual deformation by having some organized steps for material removal. Etching, of course, will reveal the grains, so there's various ways of doing this. Immersion, swabbing, electrolytic etching. There are other ones. But to make sure that we're repeatable, what's important is that a fresh solution should be used and a constant time for reproducible results. So if your etchant is been there for 2 weeks, and then you leave your sample in it for a longer time, you might end up with a burned sample, and it's very difficult to get reproducible results. So if you take for habit to change your solution every other day, and then you keep your etching time, then you should have consistent results. Now, the original definition of ASTM grain number is the number of grains per square inch at 100x. So that's the formula that we have here. And this is now used with more elaborate formula. So what's important to remember as a rule of thumb is that the higher the G number, the grain size number, the smaller the grains. That means that there are more grains that fits within the square inch. So that's the idea of the grain getting higher, similar to buckshot, I guess. It's the same principle. There's when you have more grains, more pellets into a certain area, the value increase. So that's more grains. So there are 3 major methods. Comparison method, which is pretty straightforward, that I'm sure everybody's familiar with that. So basically you look at a comparative reference. Like in this case here, this one here is something you would look in the eyepieces and you would see the individual grain size, and then you look at the live image underneath, and then you say, well, it's 4, 5, or 5.5, whatever. But there are also other methods, or we can use charts rather than just that only the eyepieces. Planometric procedure, that means that what we're doing is that we're counting the number of grains within a known area. So that's why we have a circle, and we'll go over that later on. And then the intercept procedure, which is probably the most accurate one, is where we count the intercept touching a line. So there's various approach to that. Now, if we look at the comparison chart, we can see that there's various type charts for various structures. Of course, you need to choose a structure that is representative of your material. So if you have twin grains, you have to use plate 2. And then if you have this example of copper alloy, you would use plate 3. So if we look at what the standard says is that we have a variety of plate number, 1, 3, 4, and so they're depending on the material that you like. Nickel alloy base will be 2, and normally the reference is that they're based on the 100x magnification. So that means that if you're looking at a chart, that means that you have to look at 100x to have a comparative magnification. Now, we can use automatic image analysis, and that's the purpose of this presentation. All of these all of these test methods can be applied to using an image analysis system. So it could be used for any type of grain size, but also with the benefit of using a imaging system is that you can work with non-equiax type of grain as well. So Jeffrey's planometric, that's the a fairly simple method in a sense that you make a circle of a certain size, which is 79.8 millimeter. But actually, with an image analysis system, you can overcome this size. So we'll come back to that. So basically what we're doing is we're looking for the number of grains into an area in square millimeters. So what we see in red are the complete grains, and what we see in green are the grain that are intercepted by the lines. So they're basically put in the formula. So N1 is the red, N2 is the green, divided by 2 because they're half a point. And we have the Jeffreys multiplier here that takes into account the magnification. So you could put that into a formula, and then with the log formula, but also you could just look into the ASTM chart here, table 4, where if you end up with the number of grain that you have at 90.51, that means that you have grain size 7.5. So it's pretty straightforward method that you could use. And there are other factors that you can look into it as well. The Hine lineal intercept method for single phase grain structure. It's important to mention single phase grains because normally if you make a straight line, you need to make sure that you have a single phase, so you don't end up with 2 or 3 different phases, which you would need to have various orientation of the line to make sure that you have something more random. So in this case here, the formula, which is here, would take into account the N and L, which is what we have at the top, right? So N is the number of intercept grain. So this is what we have here. And we count the grains depending on the line. And then you make the measurements, or you could use the grain border intersection, which are the segments of the lines, right? Instead of having counts, you have segment. And you end up with an average segment length, which you put into the formula here, and then you will have the grain size measurement. One of the method with the circle, so it's an alternative to the planometric that we saw earlier. So this is to continue with the intercept. So Helium method was originally developed by having a circle of a certain size, and then you basically count the intercept. So before it was on a ground glass or a monitor, but now you can do that directly on the screen where you would count the intercept, and then at the end you would measure the segment, right? The segment and the number of intercept, and you have your method. Abrams here improved that method by adding 2 other circles. So the idea of this is to have within a certain image more counts, so that because there's a certain number of grains that you should use if you want something repeatable or statistically viable. So having 3 circles gives you a more intercept to count, but also it's not limited to as much as with the planometric method, where the manual planometric method, I should say, where the orientation, not the orientation, but the grain size could be deformed. It doesn't need to be equiax because now we have a random method of counting the intercept. So we're getting into the Clemex Vision PE. So if we look at the first method that we talked about, so we have a grain size number, like in this chart here. So we have a grain size that we would look from a live image, and we would look at the grain, the chart here, and we can scroll, and the grain size value will change. So it's 8.5, but if you scroll up, it will go 9, 9.5. It normally goes to 10, and if you go down, and scroll down, rather, you will have the actual grains that are coarser. So we can see here that we have a grain size and an automatic measurement just to compare. So we have 8.7, and the chart seems to be pretty good at 8.5. So normally the idea is to have a chart if you don't have a reference to do it automatic. Here's the intercept method that you could do from image analysis. So if you have a structure that is very poorly defined, so where we don't see the boundaries, like or it's difficult to see like a twin grains, you could use the circles like this, and you just count the intercept, right? Same principle as we just saw earlier, but the measurement will be done by image analysis. So everything will be counted. So once you're done, you have a number. And then another benefit also is that you can work at a different magnification. As you can see here, we have a 200x grain. So that means that we're not limited by magnification in our calculation. On the right, we can see that we have the similar approach, but here, because the grains are defined, you can detect the grain boundaries and still do an intercept. Now, the idea here is that we use the mouse originally, but the software will detect the points at which there's an intercept and will count them. So if someone says we need to do an intercept method for grain size and we need to have the circle, you can do that automatically if you can detect the grain boundaries. Here's a different approach to line intercept. So this sample was done with the Micwade-N method. So we can see here that most of you are probably familiar with that, but so you heat up the steel at 927 degrees for 8 hours, and you put that into a carburizing environment so that the carbide will precipitate at the boundaries. And in this case here, it was electrolytically sodium hydroxide etched, and it's observed in dark field. So sometimes some material will react to bright field. Like in this case, this is better with dark field here. Now, you can see that what we're doing here is that we're just drawing the lines, right, that are representative of our surface. So a circle will not be the right approach here, because a circle here, you won't have any grains here, and you will end up with very long segments, which will throw off your values. This here, you can cover the number of lines here, and then we have about 4,000 micron here of lines, and then we count the intercept, and then we have an accurate grain size measurement for a challenging structure. Now, what I mentioned earlier is that you can detect the grain boundaries. When you can detect the grain boundaries, whether you end up with a good detection of the boundaries, and then the software will measure the grain size. Here we have two methods of measurement. This one is called an object measurement. So all the grains are measured individually. So we can see that we have classes or grain size classes, 6.5, 6.1 to 6.5, and so on. And we see the number of grains. So we have a good statistical impression of the grain distribution. So you can, when you're scanning, you can see your grain size vary. What we also have is the field measurement. The field measurement is certainly something very interesting, because you end up with measuring by intercept method. So you're measuring all the grains, and all the camera lines that you have will intercept a line that is detected and count the segment. So it will measure like this, horizontally and vertically, to end up with something that is quite accurate. And you can see the measurement are similar, 8.7, 8.8. You know, we have similar value, even though it's counted differently. Grain size measurement, we have here, we can see that we have, that's what we just talked about, right? The grain variation by object. So we end up with some statistical, so that are interesting. So we measure 57,000 grains, so it was in about a minute. Was it a minute? Yeah, about a minute. So it doesn't take long to measure something that is interesting or representative. And at the same time, we measure the grain size by object, by field rather. So you can see that for each dot is representing a field measurement. So each dot is a field measured average grain size for the field. So the idea is that when you're scanning, you can see the variation of grain size within your material. Instead of having just the distribution of the grain, this here tells you where they are because you know what's the field position. One of the benefits also that you have is that having data is important, but you don't want to be limited to having just a raw number. So it's important that you have a browser like this where you can click and see the object so that you can validate that your results are actual grains, they're not artifacts that you've missed for some reason. Not all grain sizes are easy to do. Like this is an example here where we have a material where we have a lot of noise inside, and it's very easy for systems with not too many instructions to pick up this as false boundaries. So as you can see here, we're getting quite a good results. Another challenge is with those color grain. This is for aluminum, so we don't have an actual boundary, right? So there's a color transition, but not an actual boundary. So what we do is we use add some edge finders and some color detection to be able to pick that up. Here's some new, we have a new method of detecting boundaries. So this is quite challenging in traditional methods. So normally it's actually impossible to detect automatically. And we've developed this new approach where we can get the grain size well detected. And so in this case here, it was those are stainless steel, and they were Villela's etched rather. Here's another one. It's not too easy as well, right? So we have a lot of no real boundaries. So this new algorithm makes a good job with this. Here's another one. Again, traditional threshold is it's not possible to detect that. Now this one was nidal etched. And here's another one where we have, maybe this one is a bit easier in a sense that we have more white and black kind of boundaries, but still it's very difficult to detect with traditional method. Well, these new algorithm, it's makes quite efficient. Now, this is what we talked about earlier, where we said that it could apply to various type of material. This is a foam brick. So this is like a porous foam, of course. As you can see, we can see the pores, and we can measure grain size. So when the formula that we use for the intercept, for example, could be used for this as well to measure these type of material. We're getting close to the end. So here we have this stage micrometer, which is allow us to do an auto calibration, I should say, where the software will detect the rectangles here, and then you will end up with measuring the stage micrometer. Instead of having someone doing it manually, this will be done. It will detect the 2000, and it will apply the actual measurement, 2000.5. The benefit is that everybody does it the same way. You put the micrometer on it, you end up, you run your calibration, and it's always done the same way. And there's a NIST certificate that you can have it for your audits. So in conclusions, we're conforming to the standards that are available. We have many methods that we can use to achieve the measurements. We're not limited to easy grain size. We can do some challenging ones. So we have this object and field measurement. So we have a better evaluation of the grain size throughout our material. Various threshold methods also. We're not limited to just a simple gray level method. Using a motorized microscope, we can have conditions that can be recalled. So if you have a motorized microscope that you have set a certain way, you can recall all the parameters, so you have repeatable analysis. So that's basically what we're seeing here. And then we have other applications that are available in metallurgy. So this is Q&A section, and I would like to turn it over to Vicky.
Okay, thank you, Mark, for that great presentation. We do have time for maybe one question. We did get a lot that came in, so I want to let everyone know that Mark will be responding to questions after the presentation's over individually. But could you answer this question? How many grains should be analyzed in order to have good statistical representation?
Sure. I guess generally, if you're using a manual method, the standard says that you should do 10 fields. So basically, when you're looking at the image in the field of view, you should have 50 grains. So if you have 10 fields, you end up with 50 grains, 500 grains, and then you will end up with 10% relative accuracy. So if you're doing that manually, if you're doing it automatically, basically what you do is that you look at you just run your sample, and you just look at the call this I have a blank on the name of this. Standard deviation, sorry. There we go. Standard deviation. And so when your standard deviation doesn't move anymore, you know that you have enough grain. So even if you continue after that, it's not going to be more accurate. So.
Okay, well, thank you for that. We have so many questions coming in, we won't be able to get to all of them. But in a few days, all participants will receive an email with further contact information. I encourage everyone now to complete the brief survey that will appear on your screen as you exit the webinar. With your input, we can continue to provide webinars with high-quality, practical information that you can use. I also encourage you to follow up with Mark for more information. Once again, I'd like to acknowledge the sponsors of today's webinar, Clemex Technologies. With their unwavering commitment to delivering high-quality results, Clemex Technologies builds tailor-made solutions that best suit their clients' needs. For more information, visit clemex.com. Thank you again for participating in this ASM webinar, and have a great day, everybody.